Hello and welcome to a new very interesting video. This video is about this little circuit here that I built, and this circuit is actually an FM demodulator. So you connect your FM signal to this connector right here, and then on this point on the output you get your demodulated signal. Okay, and this thing actually is a Foster Seeley discriminator. And it is also called the phase discriminator, and this circuit has a lot of nice properties that are much better than the slope detector, like a common slope detector. So this is much better than this. It has a higher fidelity and lots of other nice properties, and it is widely used in radios and such, but the thing with this is it's much more complicated, so it's not that easy to understand, and in this video I will try to explain this circuit and to get a better understanding for it, how it works. And of course after that I will show you the thing in action so that you can actually see that this thing actually works. So let's get right into it. Let's start with the explanation. Alright, before we jump right into the demodulator circuit, I will show you how the signal looks like that we are going to demodulate. Here I have my oscilloscope, my Dextronics 2467, and I've connected my signal generator, the HB8601A, to my oscilloscope. So here you can see the generator. So this is a RF signal generator, and it can do a bit more. It can also sweep the signal, and the cool thing about this is that it has a modulator built in, so you can modulate your signal with a 1 kilohertz signal, with a 1 kilohertz sine wave signal. So this is pretty cool for such experiments, because that way I can modulate it and I can see if the demodulator works, because if the demodulator works, then at the output we're expecting a 1 kilohertz sine wave. Alright, and now the modulation is off because we have this switch here to turn on the FM modulation. It also does AM, but now I turn on the FM, and now you can see here this is a bit blurred, and this is because the frequency is changing. So here's the trigger point, and since the frequency is changing, it blurs it, and that way, because the frequency goes up and down and up and down, and therefore we get this blurred image. If you want to see it a bit better, I turn on the times 10 magnification, and now you can see the signal is modulated. And if I turn it off, now you can see it's still no change, and now it has change in frequency. So this is working as it should. Again, back to the 1x, and if we go to FM, now it's changing and now it's not. And if you look up here, this oscilloscope has a pretty cool feature, namely a frequency counter. And as you can see, for this experiment I will use a 10.7 megahertz. So why do I use a 10.7 megahertz? The thing is that in many FM radios, the so-called IF frequency, or intermediate frequency, is 10.7 megahertz. So this means that if you want to receive a signal, for example, of 100 megahertz, then your signal gets received by your antenna, and then it gets mixed with a local oscillator, and the mixer, with the help of the local oscillator, mixes your signal, your 100 megahertz, down to 10.7 megahertz, and the rest of your radio has to process the 10.7 megahertz. So now the oscilloscope goes into standby, so now it's back. And the advantage of this is that your complete signal processing can work on 10.7 megahertz, and it does not have to be tunable. The only thing that you have to tune is your local oscillator. You don't have to tune any of the other components. They can be fixed on your working frequency of 10.7 megahertz. So this is a huge advantage, and since 10.7 megahertz is a common frequency for this IF, I will use it for this experiment. Of course it would work with any frequency, but since it is common, why not use it? Okay, so now let's start with the explanation of this little circuit. Actually, it's not that easy to understand. So we will build up a little bit of knowledge, and step by step we will get to the point to the point where we can understand this little circuit, and then we can enjoy it much more, because if you understand something, then you can really enjoy it. So the first step is, of course, to draw the schematic. So this is what I will do right now for you. So I will draw the schematic of this discriminator. Okay, there we go. This is the complete circuit of the Foster Seeley Discriminator, and it is not that much, but it's also not that easy to understand actually, because it's all about the transformer. You need to understand what the transformer is exactly doing to understand what the whole thing is doing. The rest is pretty simple, but you need to understand the transformer, because the transformer actually is like two LC resonance circuits. So you have here this capacitor and the L1, the primary of the transformer, and you have this capacitor and the secondary of the transformer. And this is connected. It is actually center tapped. So, and center tapped means it is actually in the center. So both sides have the same amount of turns. And yeah, it's all about the transformer. So to understand it, we need to understand the transformer. So I will start by explaining a bit more how this transformer should work in general, how you can model a transformer, because this is key to understand the rest of the thing. Yeah, so let's get right into the transformer. Okay, alright, so how do we model the transformer? So for completeness, let me just first of all draw the transformer again. So we have two coupled inductors, and let's get right into it. So to model it, we just use two controlled voltage sources. So we have here plus minus, we have plus minus, and on the output of these sources we have an inductance, of course, and a resistance, because this is what a transformer has. It has inductance and resistance. Again, on the other side we have the same. We have inductance, we have resistance. Okay, so now let's put some voltages here. The input voltage is V1 and the output voltage is V2. Again, it can be swapped because of the transformer. And now these controlled sources here, they generate the voltage. And how big is this voltage? This voltage depends on the current of the opposing side. So if this current here is I1 and this current here is I2, okay, then how big is this voltage? This voltage actually is M, which is the mutual inductance of the transformer, times di of the opposing side 2 divided by dt. Alright, on this side we have the same. We have M times di 1 divided by dt. And if we do the phasor transform to get it into the phasor domain, then we get M times J omega, and now we have just I2, okay? And on the second side we have M times J omega I1. Alright, but what is M? How can we get M? M, the mutual inductance, is computed easily. It's just K, the coupling coefficient of the transformer. If you have used LT Spice, for example, this is it also uses this K. Actually, it does exactly this thing. Times square root of L1 times L2. What is L1? What is L2? Of course, this is L1. This is L2. All right. So if we did the phasor transform right here, so we can use the complex impedance of these inductances, which will be XL1, or let's write it that way. XL1 is actually J omega L1, and this was 1. This is XL2, and this is actually J omega L2. All right. This is just resistance, so it will stay resistance R1 and R2. Okay, and since here we have a J omega and an L, because this M is actually a mutual inductance, so this is an inductance, I can also call this part here X M, and this here also X M. The interesting thing here is that the mutual inductance on both sides is the same, so we have no distinction between the two sides, but with the L's and with the R's we have. If the winding ratio is the same, of course, then it is the same. Yeah, but this is the basic model of your transformer, and to hammer that in, let me do a short example. For this example, we will find the input impedance seen on this side of the transformer if a resistor is connected on the other side of the transformer, and we will get some interesting results with that. So again, input impedance seen on this side if on the other side there is connected a resistor. So let's do that. First of all, let me redraw as on this portion of the page the transformer model. Okay, and we want to know the input impedance here, set in, if there is a resistor connected on the output, like this, and this is just, let's see, it's just RL, I call it RL. Okay, so of course, on this side, I connect the generator, okay, which generates a V in, and current will flow, and I don't call it V in, I call it V1, like that. Alright, okay, so let's start to get the impedance on this side, this set in. I just have to write set in. The input impedance is the input voltage V1 divided by the input current, in this case I1. Alright, so we are dealing with AC, so this should be a small v, but it doesn't matter so much. Okay, so let's just see what we got here. I can write that V1 is pretty simple. V1 is just the sum of these voltages here times the current. So it's actually just I1 times R1 plus XL1 and the whole thing plus XM, and now be careful, times I2. Okay, so basically this is a KVL around here. And now let's look at the output. What do we have at the output of the thing? So since the current goes in this direction, the voltages will be in this direction, but we have a little problem here. Then all voltages would be in the same direction. So actually this here must be negative, right? Because this here is sourcing this current, and the current will flow out of the plus, and since it will flow in this direction, this has to be negative. So now we can write everything. So we have now minus XM times I1, and this is equal, all of these voltages are here, and this is equal I2 times XL2 times plus R2 plus RL, and that's it. And from that we can get our current on the second side, I2, and this is then minus XM times I1 divided by XL2 plus R2 plus RL. Okay, there we go. And now we can plug that into V1, because now we have our I2. We have two equations and two unknowns. So I2 is unknown and I1 is unknown. So I can eliminate I2 by putting I2 into here. So let's do that. V1 is equal to I1 times R1 times XL1 plus XM and actually this is now not a plus, it's a minus, because this is minus. Okay, and let me put xm on top, so it's minus, and now xm times xm gives me xm squared times I1 xl2 plus r2 plus rl. There we go. Okay, and now we have v1, and what we want is set in, and set in is v1 divided by I1, so we can so I1 cancels, and I can say my set in is now R1 times xl1 minus xm squared divided by xl2 plus r2 plus zl. And this is the impedance looking into the primary of the transform. And why I'm showing you that? This is pretty simple, because I want to show you the effect of the coupling on the performance of the transform, what it actually does. So let's go back to we have this formula that mutual inductance is coupling times square root of L1 times L2. Okay, there we go. And of course our x m is j omega m, and of course our xl, so for all else, is j omega l. Yeah, but if this thing goes down to 0 because of no coupling, we only see the inductance, which is of course expected. So if you have only one coil, only one inductor, and they are not coupled by anything, then of course you have only one inductor, and this is the model for just one inductor. But as soon as you couple them, the mutual inductance goes up, so this term here goes up, and you have more and more and more effect from the second side, and in this case we have more and more of this impedance transformation. So this is very important to know this, because this is a core concept of this Foster Seeley discriminator, because the inductances inside these discriminators or in the circuit are have a lower coupling capacity, coupling coefficient. They have a high Q but a low coupling coefficient, and this is an important property because this means that we can view this side of the discriminator without interference from this source. Again, if m goes down to 0, then we have only this, and this shorts out, so we only see this right here, and this will be very important in our analysis. So yeah, let's take that and let's move on to the second part, which we have to analyze before we jump into the real analysis of the discriminator. So now let's go to the next step in analyzing our demodulator. For this we have to take a short look to the LC circuit, to the friendly LC circuit. So the LC circuit, pretty famous. It's just in this case the parallel version of it. We have a capacitor here, we have an inductor here, so we have an C, and we have an L, and here we have a connector, here we have a connector, and since we have losses, we also have to model an R in here, so this is the R component. Okay, and I want to get the impedance seen between these terminals, so I want to get the set of this, and I want to get the impedance depending on the frequency, so set of X of S, the complex impedance, where S is J omega, so omega is 2 pi F, and therefore this impedance is dependent on the frequency, of course. Okay, so now it's pretty simple because it's just parallel connection, so I have to compute the parallel combination of this. The set of S is equal to, let's see, if I connect things in parallel, then I have to do 1 over and then 1 over the components, so 1 over plus 1 over and so on. So let's do that. So what do we have for the C? What is the impedance of the C? The XC would be, what is XC? XC is J omega C, 1 over J omega C or 1 over SC. The XL would be SL, and the impedance of the resistor would be just R. So let's do that. 1 over 1 over SC gives me SC, plus 1 over SL, plus 1 over R. So there you have it. And now what I want is, I want to put it into a better form, which you can also plot easily. For this I multiply the whole thing by SRL. So this gives me set of S is equal to, on the top we have SRL, okay. And what do we have on the bottom? We have S times S is S squared, and then we have C RL, of course, plus, so this cancels, so we have only R left, but I will put it here on the end because this SL cancels, so we have R left. And what do we have here? We have SL. So I just like to write it in a way where I have S squared, S and R. So that's also easier if you want to enter it in a computer, for example, to plot the transfer function. And speaking of plotting the transfer function, if we plot this, we get the following magnitude. So this is the frequency or the omega, doesn't matter in this case. And we get this response. So this is the magnitude of Z. Okay. And if we look at the phase of the whole thing, so we still have, okay, we need to go down, we still have to, omega, this is 0, this is the phase angle, I just give it some name, and now I have 90 degrees here, minus 90 degrees here, and if we plot this, then we get exactly this here. And so this is the impedance of our thing, and this is the phase, so this is the body plot of the whole thing. And I hope you can read it on video. I will move the paper a bit up like so that you can see both. And the thing here is that at a certain frequency, at the resonance frequency, F, I call it just F res, this is the frequency where the XL and XC is the same, but since they are opposing each other, because this is, if I write it differently, if I say XC is J omega, or it's just minus J J omega C, because this is 1 over J, so this S is J omega, and if I compute 1 over J, then I get minus J, and this XL is just J omega L. And so if both impedances are the same, then the minus and the plus cancel each other, and therefore we will get an infinite impedance. The only thing that's limiting our impedance here at this point is the R, because these two are infinite, so they are out of the picture. So we have only the R right here, and this is what limits this peak right here. And there's also this famous formula, the Thomson formula, or the Thomson formula, which if you just equate these two, then you get a certain omega, and this omega will be 1 over square root LC, and so we get also omega, I call it omega res, and we get also F res, and this is 1 over 2 pi square root LC. So this is how you get the resonance frequency. Actually, it's extremely simple to do. Just set this equal to this here, and then search for the omega, then you get the omega, and there we go. Okay, alright. So this is for the frequency response, and the phase response is also interesting. The phase response is as follows, that at resonance it has 0 degree, the impedance is 0 degree of phase response, and below resonance we have plus 90 degree, and above resonance we have minus 90 degree, which is also pretty simple because of course above resonance the current flows through the capacitor, and in the capacitor we have this minus J, so we have a minus, so we have minus 90 degree phase shift. And above the resonance case, below the resonance case, we have plus 90 degree, because then the current will flow through the inductor, and the inductive current has this J without minus, so we have plus 90 degree, and that's why we get this phase response right here. Alright, so now let me give you another intuitive thing for this phase shift here, because we need it later on. Let me rewrite this impedance here, this Z, and I just write 1 over J omega C, so I replace the S with the J omega, and 1 over J omega L plus 1 over R. And what I will do now is the following: I will just group these J's here, so I can rewrite this to 1 over R plus J times, and here we have omega C, and this is 1 over J, so it gets minus 1 over omega L. Alright, and maybe this gives you a pretty good view of what's going on here, because if the frequency is low, so if we have a low omega, then we have here a small value, and here we have a small value, but since we're dividing a small value since we're dividing 1 by a small value, this here gets pretty big, okay, and then we have a big negative thing here, so this becomes negative, so we get a negative J right here, but we have 1 over J, so we get the positive J, which means plus 90 degree, and vice versa. If this here is big, then it for high frequencies, if this is big, then this term here gets pretty low, this gets big, then we have a big J, and 1 over, then we have a positive J, and 1 over this positive J gives me negative, and then we have negative 90 degrees. Okay, so this sums up the LC circuit, and now we can get right into the analysis of the complete thing. So this analysis will involve everything which we've learned so far, and I will start with the voltage on this inductor right here on L3. This is the voltage on L3, which is called V, or which I call VL3. Okay. So let's see if we can get VL3. How big is VL3? So since this is in the center, I will start drawing at the top of the circuit, and let's see if we can draw a equivalent circuit just for the voltage on L3. So of course, to draw that we need to get our L3 right here. Then down here we have C4, and this goes to ground because of this connection right here. Then here center tapped, and then we go to this capacitor, which I've called CC, like C coupling, and then we have this voltage source here. So basically parallel to this is this voltage source here, connected to this point here, and having this V in across it. Now our question is, how big is the voltage across across LC, which is VL3? How big is it? So this of course depends on how big are these capacitors, because if they are big, then they have a small resistance or a small impedance, and if they are very big, then the impedance is small in a way that the voltage across here will be almost the voltage across here, because this is a simple voltage divider. Let me just write it down here. We have VL3 is equal to the source voltage V in times XL3 XCC plus XC4 plus XL3. So we have XL3 here and here, and from this we can see that if these impedances are very small, then it will be approximately V in. And this is the case because actually this here, this detection diode will be filtered, or the output of this diode will be filtered with this capacitor here, and so they have to be an RF short. And this capacitor, the only job of it is to connect the primary with the center tap of the secondary, and it should be also short for AC. So these two are very small, very small, yes, small in this case, big capacitance, small impedance, and therefore the VL3 is V in. There you go. Okay, VL3 is V in because the capacitance are pretty low. So this completes the first part of our analysis, and the next step is to analyze the transformer. So for this I will let's see how big the current is that flows into the transformer, into the primary of the transformer. Okay, so let's do that. I just call this current which flows into here, I call it I1. And how big is our I1? Okay, let's see what we've learned so far from our transformer experiment. Since this thing has a low K, low coupling factor, and a low mutual inductance, this means that we don't see much of this opposing voltage source here. We only see these components here, but we don't see much of this guy right here. So we can ignore it and we can work with these two, and I will only work with this one, with the inductance, because resistance is quite small. So I will only work with the inductance right here. So my I1 on this side here will be, I1 will approximately be just V over the impedance. So this is just V in over the XL here on the primary side, and this is J omega L1. So this is the way how we can get our input current here and how we can get our phase shift. Again, the important thing here is that this transformer is loosely coupled, and therefore we can do this approximation that the input current is the input voltage divided by J omega L1. We can do this approximation. The correct way, of course, would be to include this opposing voltage source. So basically then it would be this input voltage minus this voltage. It gives me the voltage across this inductor right here, and to get the current I have just to divide the voltage by its XL. But for this here, this approximation is good enough and very important. So this is the first important thing if we think about this transformer. Okay, so now the next step is, let's compute the output voltage of the transformer. So the voltage on the secondary side. If this V in is also the V1, so I call the secondary side the V2, like this, and I will move this here. So, and now let's see if we can get the voltage V2. What is V2? V2 drops about across this capacitor here, this capacitor C2. So I will draw another equivalent circuit. And where is this C2 connected from the transformer point of view? We connect this C2 to the secondary of this transformer. So I can just draw this right now. I have my R2, I have my XL2, and here plus minus I have my M times J omega I1. I'm always switching between capital and small i's. Actually it should be a small one because it's AC, so small I1, and I also put small I1 here, and I will put it also here. Yes, that's the more correct way here. And now let's see what is this voltage here. It's again, it's just a simple voltage divider. So actually, this voltage here should have a name. I call this voltage here V secondary output, because secondary of the transformer. Just to give it a name. And now we can apply voltage divider to get the voltage 2. So V2 is equal to V secondary output times. Now we have a division going on here, that the output voltage drops at XC2, and the complete thing is XL1 plus, XL2 plus R2 plus XC2. So there we go. This gives us the voltage on this side. So what can we do with that? We can substitute VSO back. So what is this actually? This is actually mj omega I1, but we also have a formula for I1. So let me plug everything into one equation. So this would be then, and of course the thing is here, it also depends on the currents, but if I count this as positive current flowing out here, then it's opposing this side here, so I have to do a negative for this here then. Okay, then this would be minus mj omega I1 is times V in divided by j omega L1. Okay, so this is this V input voltage here, and then it gets multiplied by what we had before, XC2 XL2 plus R2 plus XC2. Alright, and there is a lot of stuff which cancels. This j omega cancels, this cancels, L1 remains, V in remains. Okay, so this should be right. And now I will change this equation a little bit, so that it might be familiar of what we have seen before. And for this I will write the following thing: V in times m over L1, and we have 1 over, and of course the minus, 1 over j omega C2 divided by, and what do we have down here? We have something similar which we had by the for the LC circuit. We have R2 plus, and what do we have here? We have XL2. So we can do the same manipulation, and we can say that this is J, and for the XL we have omega L minus 1 over omega C. There we go. And of course this is C2 and this is C2 as well. And now what remains here is that this J here is 1 over J, so we can change it as follows. So 1 over J is minus 1. So we can write the J in front of this. So we have J times this. And what does that mean? Sorry, what does that mean? And what does that mean? The thing which we can see quite clear in this equation is that at resonance, if the impedance of the inductor and the capacitor is the same, this here becomes 0. So we have no J here, and here we have this J. This J stands for 90-degree phase shift, and this now means that at resonance we have 90-degree phase shift because of the J. And the thing is that if the frequency goes above resonance, then we have the effect that this minus thing here, this if it goes higher, then this term here becomes lower. Okay, so this becomes here, this here becomes bigger. Okay, then we have a positive J right here, and So we are shifting more than 90 degree. Okay. So, and what can we see from this? If this circuit is at resonance, okay, then this impedance of the inductor and of the capacitor will be the same. So this will cancel out and will get 0. So this J will be removed. And the only thing that's left is this J here. And this J means 90 degree phase shift. So if this circuit is not in resonance, the voltage across the secondary is in resonance. If this circuit is in resonance, the voltage across the secondary of the transformer will be 90 degree out of phase of the voltage on the prime of the input voltage. Okay, and this is a very important fact. And this is just because of the loose coupling of that thing. If this would be a transformer with strong coupling, with a high K, then we don't have this effect. We only have this effect because of the loose coupling of the transformer. So this is the important part, or this is the main part why this thing works. It only works because of the loose coupling, and because this loose coupling introduces this phase shift. This is the key thing about this. And it's in many literature I found this not being mentioned as clear. So this is maybe the hardest part to understand why there is a phase shift, and this equation gives you the reason why there is a phase shift. So now with this we already know a lot. So now we know that the voltage on L3 is in phase with the input voltage. So if I draw a diagram, we have VL3 right here, and the U2, the voltage across this thing here, is out of phase by 90 degree. So we have 90 degree here. This would be U2, and actually we are looking at the voltage between here and here. So this is V2 half, and here on the other side we are looking from here down to here. So we have negative V2 half. Okay, so this is the voltage relationship of this thing at resonance. All right. So, but now let's see what happens. What happens with the voltages across this output here, across the capacitor here. So actually, the upper side is always easier to understand. Actually, we have a voltage source here. So this is the transformer, which has this V2 half on here. And we have the voltage of our inductor here, which is the VL3. And actually these two voltages are add up and they are getting rectified by the diode and then detected by the capacitor. So the sum is just a vector sum of these voltages, and this will be this voltage right here. All right. So this voltage I will just call it V3, and this is the voltage which will be across here. V3. Okay. V3. For the other side and the other diode, the same will happen. Here, also this voltage here, which then I will call V4. V4 will get rectified, and here we have our V4 right here. Okay, so at resonance, these two voltages are the same. Alright, so V3 and V4 are the same. So no diode has a higher output than the other one. But if now we are above or below resonance, as you can see from this equation, the phase of the output will change. So actually this thing here will move. So it will move in this direction, for example. And if it does that, then we can conclude from that our vector sum will also move in this direction here, and on the lower side in this direction here. And now we can clearly see that the V3, so the output from this diode here, will be bigger than the output from the lower side of this thing. and this will give us demodulation, because now we have a voltage that depends on the frequency, which is exactly what we need, because it is frequency modulated and we want to get a changing output voltage by a changing frequency. And this is what this circuit here gives us. Okay, so this was a quick explanation of how this circuit actually works. And now let me show you the thing in action. So how did I build it actually? If I zoom in a bit, so here you can see the circuit again. And as a transformer, I've used a binocular core transformer, so a core like this here. It's called binocular core because it looks like a binocular, if you can see it. And to get the looser coupling, I've wound the windings on both sides here, not around the core, but on the outer shell of the transformer. Not like this. So here you can see this is around the core. Here you can see the wire goes around the core, okay, and on this one here you can see it's on the outside of the transformer, and this gives me a lower coupling. So this is what I did to decrease the coupling. This core I think is a BN61. Yeah, and the rest here you can see the output filtering and the detection diodes. And here on the input you can see a transistor. This transistor is in common base configuration. So this means that the input from my signal generator is connected to the emitter, and my generator has a 50 ohm output impedance, and to get impedance matching, so to get 50 ohm input impedance on the transistor, I have computed it in a way so that the input impedance seen from the transistor, which is 1/Gm in parallel to the emitter resistor, which is basically 1/Gm because the emitter resistor is quite large. So I have computed that 1/Gm gives me 50 ohms, and therefore I get 50 ohms input impedance from this thing, and everything is impedance matched. But now let's look at that thing in action so that you can see what it actually does. Okay. Alright, so here the circuit is connected to everything. And one important note when building such things, because this can be troublesome maybe, is that if you use an oscilloscope probe, the oscilloscope probe you're using has a capacitance, even if it's a times 10 probe, and therefore it's loading your circuit. So if I connect my probe, for example, in parallel to this tuning capacitor here, so these are the two capacitors which can be tuned from the primary and secondary side. If I load the output of the transformer with the probe, then I have a problem because I detune the transformer, I detune the capacitor, the LC circuit. And not only detuning it, if I connect it somewhere else where the impedance is quite high, then the low impedance of the capacitor, of the input capacitor of the probe and the oscilloscope, can also load it down. So you have to be very careful when working with RF circuits to make sure that there are no loading effects. And now I've hooked up my probe at the output directly where the filter capacitors are, and this is not a problem because there are already a lot of capacitance to filter the signal and to get my 1 kilohertz signal back, so I can hook it up here. But for probing inside the circuit I've used something different, and now let me show you what this is. So let me zoom out, and this is what I've used for probing the circuit. And this is a self-made active probe, so here here you can turn it on and off, and on this output here you connect the oscilloscope, you switch it into 50 ohms, and this thing has an extremely low capacitance. Actually the input is done via a capacitive voltage divider, and one side of this capacitive voltage divider is actually this capacitor here, and this is made of FR4 board with copper, so with copper, so like boards like this, and this has an extremely low capacitance, and therefore it has extremely low loading on your circuit. And I've used this to experiment and explore it a bit more without disturbing it so much. But since this video is already quite long, I will show you just the outcome directly. So back to the circuit here. So what I can probe now is the input, the 50 ohm input, and the output. And now I'm currently connected at the output. Alright, so the output of the circuit is connected to the oscilloscope, the input to the signal generator, and let's move to the oscilloscope to see what the circuit is doing. Okay, so here we're looking at the output of the demodulator with this oscilloscope here. So the oscilloscope is connected to the output, and this signal generator is connected to the input. FM is off. I have already adjusted the signal generator to the exact frequency, and I've also tuned the capacitors or the LC circuits on the demodulator by adjusting the capacitors to the right frequency. And FM is off, and we already see nothing, and this is how it should be because we have no modulation, and this is AC coupled now, by the way, AC coupled, so we are here at the center, and since there is no modulation going on, we have no output. And now let me turn on the FM, and look at that. Isn't that amazing? Now here we have our demodulated 1 kHz sine wave signal. This is actually 1 kHz because it's modulated. It's also on here, and if you look at the time base, it's 1 kHz. And look at that, isn't that amazing? It's working extremely well. So we have a clean demodulated signal, how it should be. If I turn it off, here we see nothing. If I turn it on, here we have the demodulated signal. Isn't that amazing? So this thing works perfectly fine as expected. Works perfectly fine. And in addition to that, I want to show you something else. So I turn off the modulation again, and now I go into DC coupling. And in DC coupling there's also something interesting going on. Now we have a certain DC offset voltage, and if I adjust the frequency on the signal generator, it of course changes the DC voltage, and this is expected because it converts frequency into voltage. So this also works with low frequencies like this or DC voltages. So here I have a perfectly valid frequency to voltage converter. Look at that, isn't that amazing? And it's pretty sensitive. A slight change here produces a voltage change on the oscilloscope. And this sort of discriminator is also used for such stuff. It's not only used to demodulate FM in a radio or so. This can also be used to control the speed of an electromotor, because with a tachometer generator, a motor can produce, or the tachometer generator can produce a frequency which is proportional to the speed of the motor. And if you feed this frequency into a discriminator like this, it must be tuned for lower frequencies than this, of course, but if you feed it into a discriminator like this, you get a voltage proportional to the speed of the motor, and with this voltage you can then regulate the speed of the motor. So you can compare it with another voltage or something else, and then you can regulate the speed of your motor, which is pretty amazing. For example, the Nagra tape recorders, the Nagra 3 recorder, uses such a speed control. It uses such a discriminator in it, which checks the speed of the motor via frequency and then regulates the speed of the motor. So you can also use it for such more low frequency applications. Absolutely amazing. And yeah, now you have seen all the tests, and as you can see, it performs pretty good. There's one thing to mention, and this is that the input stage should be some sort of limiter to give it a constant amplitude, because it's still sensitive to amplitude variations, and we don't want to decode amplitude variations. We don't want to have any effect of the amplitude, because this is one big advantage of FM. The big advantage of FM is that if there's any interference in the amplitude, then it won't affect your output, because the signal is encoded in frequency changes and not in amplitude changes. But this circuit is susceptible to amplitude changes. To remedy this, you can use a limiter amplifier at the input stage to make sure that you only get a certain amplitude and that it does not get bigger or smaller, okay? This is not implemented at this one here, but this is just because it's for the experiment. That mentioned, the overall performance of this was really good, as you have seen, and I have really enjoyed building this thing and exploring it. And I hope you have enjoyed watching this video and maybe learned a thing or two. And so I will conclude this video right now, and I can just say thanks for watching and bye!